We're now going to show you how to use Gaussian elimination to solve a matrix problem. And so the idea here for Gaussian elimination is to use row operations to put the matrix in row echelon form. Then solve the resulting system. So if we're in a system already, we convert to a matrix, an augmented matrix, put it in row echelon form, and then convert it back and solve using back substitution. So we already have a problem set up. We have 2x plus y minus z equals 7, x minus 3y minus 3z equals 4, and 4x plus y plus z equals 3. And the first thing we're going to do is turn this into an augmented matrix with a 2, 1, minus 1, 7, 1, minus 3, 4, and 4, 1, 1, 3. And so my goal is to get a 1 right here. So I'm going to take row 1 and I'm going to swap it with row 2 because row 2 already has a 1. There's other things I could do. This is just the most straightforward. So I've now swapped the rows. The second thing that I'm going to do, and I'm going to do this twofold. In fact, I should have given myself a little bit more room. Let me rewrite this matrix a little bit bigger, because this is how I like to save space. 2, minus 1, 2, 1, minus 1, 7. Nope, we just swapped you. 1, minus 3, 4. 2, 1, minus 1, 7. And 4, 1, 1, 3. And so my row operations, I'm going to do two of them at once because I'm going to use different rows to do this. I'm going to take a minus 2 times row 1, add that to row 2, and store that in row 2. And the reason I'm doing that is I need to get rid of this 2, so I'm going to take the number, change its sign, so it goes to a negative, and then put that underneath the 1. And then I'm going to do the same thing, minus 4 times row 1 plus row 3 gets stored in row 3. So now here's why I wanted the room, because all I'm going to do to make this a little bit easier is when I do my minus 2, I'm just going to take this and I'm going to change its sign and double it. And I'm going to do the same thing here, minus 4, positive 12, negative 16. So now I'm going to come down and I'm going to actually write my results. I still get my 1, minus 3, 4. Now I get a 0, 7, minus 5, minus 1, and a 0, 13, 13, minus 13. Now looking at this, now that I've got this piece done, I'm actually going to ignore the first row and the first column of what I'm looking at. But it's interesting because I don't have a 1 to put here yet. However, look at the third row. What happens if I take the third row and multiply it by 1 over 13 and store that in the third row? So if we divide by 13, 13, and 13. Now we get a 1, minus 3, 4, 0, 7, minus 5, minus 1, and a 0, 1, 1, minus 1. Now we're making some progress. We still need to get a 1 right here. So what we're going to do is we're going to take row 2 and we're going to swap it with row 3. So that gives me 1, minus 3, 4, 0, 1, 1, minus 1, and 0, 7, minus 5, minus 1, and we get our augmented matrix. Now we're going to take minus 7 times row 2, add that to row 3, and store that in row 3. That's going to give me a minus 7, a minus 7, and a plus 7. Well, when we do this, this is going to give us a 1, minus 3, 4, a 0, 1, 1, minus 1, and a 0, 0. Notice that this, by the way, was also a 0. That's why we need this one to be a 0 before we can go any farther. Minus 12, 6. So it turns out that our last row, in order to finish this problem, just need a little bit more space. We're going to have to take the last row, row 3, and multiply it by 1/12, by a negative 1/12, because now the goal is to get a 1 right here. And we're going to store that in row 3. So our matrix is going to look like 1, minus 3, 4. 0, 1, 1, minus 1. 0, 0, 1, minus 1 half. So when I rewrite this, so now it's in row echelon form. I rewrite it as a system. X minus 3y minus 3z equals 4. Y plus z equals minus 1. And z equals minus 1 half. Well, we know what z is. To get y, we do y minus 1 half equals minus 1. If we add a half to each side, that gives me y equals minus 1 half. I come back up to my original. X plus 3 minus 3 times a minus 1 half minus 3 times a minus 1 half equals 4. So that's x plus 3 halves plus 3 halves equals 4. X equals x plus 6 halves equals 4. X plus 3 equals 4, so x is 1. So now I know that my x is 1, my y is minus 1 half, and my z is minus 1 half, and I get the point 1 minus 1 half minus 1 half, and that is the solution to my original system.